All right. Hello, everyone. I see there's already a question from Professor Matier's last lecture uh, for the coupling of rotations in three complex dimensions and the Young tableau. What is the reason from going from the element in tensor product space to a direct sum of spaces? So it's getting to the heart of kind of group theory, which don't really want to spend too much time discussing. But essentially, what you're doing is you're taking a combination. So you're taking two spaces of elements, and when you do this this product of these two spaces of elements, you can think about like different blocks, and you're trying to reorganize the blocks into different what are called irreducible sets. So that just means some prepackaged combination that has some specific properties. So if you take this product of these large spaces, multiply them together, and find all the different combinations, you'll have some combination A plus another combination B plus another combination C. That's kind of a physical motivation behind these tensor product spaces going to a sum of different spaces, because you're just finding all the what are called irreducible blocks or irreducible sets. So I won't say much more about it, but you can look into irreducibility of tensor product spaces in group theory for more information.
Andrew, maybe we should start by introducing yourself to the people
sorry,
that maybe haven't seen you before.
Yeah, I had the question, wanted to answer it.
Do you want me to introduce you, or you want to introduce yourself?
Either way, you're on camera, so.
All right, sounds good. So hi everybody. As you probably know, I'm Raul Briseño. I'm a little under the weather, or at least I have like some sniffles. So I'm not gonna stay here for all that long. But Dr. Andrew Jacura, he's a postdoc here in our group at Old Dominion University and Jefferson Lab. He's an expert in particle and nuclear physics with many different expertise, and he's lectured in the past for the REYES program, and he's part of the REYES nuclear mentoring program, and so he's going to be lecturing this week. So you're just going to be interacting with him. I'll stay in the backgrounds. I'll just get out of his way. So you're in good hands. Have a good time. Thanks again, Andrew.
Thank you, Raul. So yeah, I'll got excited by a physics question and I had to answer it. So I'm going to be lecturing on some various topics in scattering theory, essentially building on some of the groundwork that Raul and Vincent in their previous weeks have laid out about QCD and hadrons and kind of the physics we do. So I can share my screen. I hope, yep, I can. And let me make this full screen. So I'm calling this kind of set QCD spectroscopy. And the goal of this Zoom thing is getting in the way and it's bothering me. Let's try again. Yeah, sorry. Yeah, so now it's to kind of build off these ideas about all these different scattering experiments in the past that have given us a lot of information on how the strong interaction physics works, and how we can learn some very cool properties about nuclei and hadrons. I'm going to kind of break this up into over today and Thursday, talk roughly about the general ideas of what QCD spectroscopy is, and kind of introduce our case study that I'll be referring to the entire time of the deuteron. The deuteron is the simplest nucleus that we have, and even this simple case here, you can learn a lot about how low energy nuclear physics works, and kind of how these nuclear forces interplay, and how we can do QCD spectroscopy in general, but using the deuteron as kind of our example along the way. we'll introduce some notions for reaction kinematics. So if you have some particle collision, kind of what are the relevant degrees of freedom? And this is, obviously what kind of comes to mind is energy and momenta. We're then going to connect these nuclear reactions to these scattering amplitudes, which were introduced by Raul in the first set of lectures, where you measure some experiment, some beam colliding a target, and you get out some data. We would like to connect that data to something theoretical, and that theoretical object is the scattering amplitude. From the scattering amplitude, we can now do spectroscopy, which ultimately just comes down to identifying the states of the system in the interaction that's occurring. And then we'll look at the neutron and proton scattering system and how it relates to the deuteron. So that's my general plan for doing this. And again, we have, sorry, Zoom is horrible with all these pop-ups. So let me first kind of start just motivating the general ideas of what spectroscopy is. We've been doing this for a long time now, studying the spectrum of various different phenomena and understanding what kind of what physics comes out from this. And kind of the prototypical example that we tend to think of is using the hydrogen atom, which the hydrogen atom led to the discovery of quantum mechanics and this whole breadth of particle physics eventually. So originally, you may have learned in, say, chemistry class about the hydrogen spectrum, which you can generate by taking hydrogen gas. So this would be molecular hydrogen gas that you ionize, and it emits some purplish light. You can collimate that light into some sort of on some sort of target. In this case here, it's just a prism, which the prism acts to separate out the different components of the hydrogen gas into its kind of fundamental properties, fundamental modes, fundamental attributes. These fundamental modes is what we refer to as the spectrum of the hydrogen gas. And in this case here, it's just different wavelengths that make up the purplish gas we see. You can break it up into its different spectral lines, and these are the quantized energy levels that you should probably have seen in chemistry. I think at least most people should have seen by now. So this hydrogen emission spectra, you get these line emissions, red, blues, greens, and violets in the visible spectrum. And when this was first discovered, this was kind of unexpected based upon the prevailing classical theories of the time, so electromagnetism and Newtonian mechanics. So some explanation was needed for this, and that ultimately led to the formulation of quantum mechanics, where you have some system that you describe generally by a Hamiltonian, which the Hamiltonian is just a fancy word for just encoding all the dynamics of the system. The Schrodinger equation is the fundamental equation of quantum mechanics, which governs how systems evolve in response to some interactions. And you can, if you've taken quantum mechanics before, you know that you can solve this type of systems for the properties of some physical phenomena. So in the case of the hydrogen spectrum, you have a proton with an electron orbiting it. You encode all the dynamics of protons and electrons interacting into a Hamiltonian H. And when you solve the system, you can get the energy spectrum out from this. Now, I'm going to stop again because for some reason, my mouse is not showing up, and I don't like that. There we go. It should probably do it. Yeah, sorry for all this back and forth. There we go. All right. So the Schrodinger equation, again, is the quantum mechanical equations of motion, essentially, that describe how the system evolves. And when the pioneers of quantum mechanics took all this data from the hydrogen spectrum and kind of formulated how quantum mechanics ought to work. They can then predict what the spectrum should be. Here they get a bunch of energy levels governed by some fundamental parameters, m, the electron mass. Alpha here is related to the electric charge. It's called the fine structure constant, but it's just, it's the coupling between the electron and proton electromagnetic forces. And then you have some quantum numbers, which quantum numbers are some general sets of numbers that classify the system. And you can plot what the spectrum of the hydrogen atom is here, and you get various different energy levels. The ground state being the 13.6 binding energy of the electron to the proton. And you get an infinite tower of states with various different quantum numbers that describe its angular momentum until you reach the ionizing region, where you can kick off the electron from the interacting proton and just have some free electron system. From these energy lines, you can then compute differences between them, and lo and behold, you get exactly the wavelengths needed exactly the wavelengths out that you find when you experimentally measure the hydrogen spectrum. So, spectroscopy is really this way of classifying all these different phenomena we're seeing as we break up a system into its fundamental parts, and trying to understand all these different features that go into these underlying interactions. So with simple electromagnetic interactions, we can get out various different energy levels from all these different interacting states, along with their quantum numbers, which are just a set of conserved numbers that describe and classify the system. You see there's a question here. What does it mean that the binding energy is negative? So if we think, in this language here, if you have a proton and electron just sitting still, not talking to each other, you can think about the kinetic or the kind of energy between these two. And if we set the non-interacting energy to 0, if the electron and proton start talking to each other and they bind to form some sort of bound system, we just call that negative energy. So a negative energy just means that the system is bound to a lower energy state, and you need to put energy into the system to break it apart. So if you have a hydrogen atom and you want to ionize it, you need to hit the hydrogen atom with photons of enough energy to break the electromagnetic bonds between the electron and the proton. So when we talk about negative energies here, it's really just the binding forces between, in this case, the proton and electron. But the same thing happens in strong nuclear forces as well. We'll call, some energy, if a system gets bound, that is, you can make a new lower state system by putting two objects together. We'll call that the energy that binds them as negative, and you need to put that energy in order to break them apart. All right, so I hope that answered the question. So, we started off with some experiment, formulated some theory, calculated a result from the theory, it matches experiment. Yay, that's all good. But then you can do more and more precise experiments, and you'll find, whoa, there may be in the spectral line shapes, you'll find that there's actually not exactly predicted. There could be small little corrections that need to be made. And this is exactly what happened in the case of the hydrogen atom and the development of quantum mechanics. But this in turn fed back into theoretical development. And we knew that quantum mechanics was not complete unless we took into account relativistic effects. So that's particles moving at some substantial fraction of the speed of light. And you get correction factors to the energy spectrum, which then feed back into examining the spectrum, learning more about it. So it's this really nice synergistic relationship between experiment and theory when understanding the spectrum of particle and nuclear physics. So if we go to QCD spectroscopy and what Dr. Briseno was presenting, you have the strong interacting spectrum, which is composed of many hadrons, and Dr. Mathieu last week gave a very nice overview on kind of the development of how we understand the quarks and the hadrons that they ultimately form. And you have, and I stole this directly from Raul, where you have some beam of particles hitting some target, and then that something happens, and then you detect it in some sort of detector, which goes to your bank of computers, and you can start analyzing data. So the number of events that happen, you can measure them. You can relate the number of events to some observable, which we tend to use the cross section, which again, Vincent talked a lot about what these cross sections are and kind of how we should think about them. And then in turn, these cross sections are related to the scattering amplitudes. The scattering amplitudes are the things that you would either want to compute quantum mechanically from some theory. So this is the ultimate goal that we have as particle nuclear physicists. And this is the case in quantum electrodynamics, where you have some theory, you can do some calculation with some very useful technique called perturbation theory and calculate effects order by order. And this is exactly what this is showing here, that you can calculate some observable to some order and some parameter which governs the interactions. And if the parameter is small, as it is in electrodynamics, you can add on correction factors that only do small little shifts, and you can compute some observable. So this is what you could do in, say, quantum electrodynamics or the high energy behavior of the standard model, and it works rather well. If you want to study low energy physics of the strong interaction, so this is the hadrons and nuclei, the QCD quantum chromodynamics, the theory, as Raul mentioned, is a very strongly interacting theory. You have these nonlinear couplings between the quarks and gluons, or between the gluons themselves, and the couplings between the quarks. And doing perturbation theory just doesn't really work when you want to do low energy physics. There are ways to circumvent this. I won't talk about them here, but you could, in principle, calculate or constrain the scattering amplitude from a technique called lattice QCD, which is a way to non-perturbatively estimate observables using Monte Carlo techniques on a computer. In practice, the techniques you use for lattice QCD follow the principles of scattering theory, which scattering theory is the overall study of how reactions work and what are the general features of reactions, independent of any sort of underlying theory that governs the interaction. So while I'm going to present it from a point of view of we don't have a theory, but we want to learn about the scattering amplitude, and then from the scattering amplitude, can we learn something about the interaction, which is the viewpoint I'll present here. The same techniques apply to calculating these things theoretically. There's just not enough time in the world to talk about everything here. So our focus here would be really just understanding this object, the scattering amplitude, and what the physical content of it is. So if we look at an example, here we go for a more complicated example before we turn our attention to a simpler case, which is the Pionucleon spectrum. So the nucleon is kind of a shorthand term for both a proton and a neutron. The pion is another subatomic particle that interacts strongly, and you can create a beam of pions from some experimental device, aim those pions at some proton target, they will hit, and then some interaction happens, and you can change the momentum of the beam to whatever you want. And when you do that, you can measure your number of events and convert that to a cross section. And this is what you see here. You see the cross section for a pi plus, which is a positively charged pion hitting a proton, and then a negatively charged pion hitting a proton in blue here. And you see many cool features that are happening in the spectrum. You see these peaks, which at first, if you compare it to what's done in, say, lower energy atomic physics, these peak, you see some peaking behavior which corresponded mostly to these line shapes, or to these spectral lines that you found, say, in the hydrogen spectrum. But here, these lines are very, very broad. They're not as sharp. They're maybe not as structurally independent from each other. There's a lot of cool little things happening in here at very high energies. These bumps seem to go away. So, we want to understand what's going on in this cross section here, and that is the job of us as spectroscopists. Now, the cool features about these bumps here is that they generally, this is not always true, but we can think about these bumps as indicating the existence of some sort of quasi-stable state. So these quasi-stable states, I think you've heard before, are called resonances, which are states that exist for a very short amount of time before they decay. And some examples here, this peak here is the delta 1232. 1232 is just indicating its mass. The delta particle, which was talked about last week, is just a bigger cousin of the proton. It's got a couple different quantum numbers that are distinct from the proton, but nonetheless, it's a strongly interacting particle that is a quasi-stable state of a pi and a proton. There's another state here, which is hidden inside this kind of well, which is called the N star 1440. And it doesn't really matter too much about what its name is, but it's just another state. And I point it out just because this general idea of peaks versus non-peaks being the distinction between having a quasi-stable state and a not quasi-stable state are kind of indicative of the fact that we need to do a little bit better job than just kind of identifying, oh, this peak is here, its mass is roughly this. We need to really go into and understand the structure of the scattering amplitude in order to quantify these different pieces here. And that, as I was saying, is our job as spectroscopists. So what we do is we use general principles of scattering theory in order to constrain what this object has to look like. And one of the things we get out is that we can identify that from the scattering amplitude, we can identify the existence of states or hadrons. So we'll use the term hadron states kind of interchangeably here. These composite states that are formed from smaller mass hadrons, in this case, these quasi-stable states, you can have states that live forever, I'll generally go under the name of bound states. So they're bounded by some strong interaction between the pion and the proton. So the key idea here is that if you look at the scattering process, so you measure some scattering amplitude, you constrain what the form of the scattering amplitude is, you can then use experimental data to identify where the bound states are of your interaction. These bound states constitute the spectrum of this interaction. So this here is the spectrum of the pion and nucleon interaction. And in general, near these kind of places where bound states exist, the scattering amplitude has a generic form where it goes under the umbrella term of a pole singularity, which is a fancy term for the scattering amplitude diverges near the point where the hadron is. And it diverges in a form that is universal, where if the energy of the interacting system gets really close to the hadron mass, which I call m here, plus the complex number I, and we'll talk more about complex numbers, I'm kind of just giving a preview here, times this factor of gamma over 2. Well, what's this gamma over 2? Gamma is a quantity called the decay width, which is just related to the lifetime of the hadron. So the lifetime here are denoted by tau, and it's equal to the inverse inverse decay width. This factor of 2 is just a convention. There's some reasons for it, but we won't get into it. So generally, when the energy gets close to m, positive m plus this decay width over 2, then this function will be going like 1 over 0. And when it goes like 1 over 0, the amplitude shoots up to infinity. And you can see kind of the effect here that since this is measured at real energies, when the energy gets close to the mass here, you get an enhancement because the denominator becomes small, and there's an enhancement near the place where the bound state exists. Now, this is a very kind of simple picture, but in general, mathematically, this is true. When you have a bunch of interactions and states happening all kind of in the same location as it's happening here, you get a bunch of mixtures of different things happening. But ultimately, you can still describe all of these hadronic states as this type of form of the scattering amplitude. So the idea here is that we have some data. We take that data and constrain what the scattering amplitude is. We use general principles of scattering theory to reduce the amplitude into some manageable form. Once we then take data and fit some parameters, which we come up with as some physical parameters or something that represents something physical, we can fit the amplitude to the data, and that will be the subject. I'll talk a little bit about that on as far as an application on neutron-proton case next time. And Andre Walker-Loud will discuss some details about fitting. I think next week, maybe it's the week after. Whoops. So once we get the scattering amplitude, we can then look at the mathematical form of the scattering amplitude and look for where the denominator goes to zero or becomes small. And we can then identify what the hadron mass and what the hadron decay width or hadron lifetime are. So that's the general procedure of how we do spectroscopy. And in this case of the Pionucleon spectrum, here you see a few bumps, but when you follow this kind of exercise rigorously, you get a whole mess of states with different quantum numbers. So in spectroscopy, it's not just about identifying just the mass and the lifetime. We also want to figure out kind of what its total angular momentum is, what's its parity, all these other quantum numbers that Vincent talked about, so isospin, flavor quantum numbers, so on and so forth. And we can identify the structure and classify how these hadrons and all these different patterns that form here. So here you see the nucleon, and then its a heavier cousin, the N-star 1440. You see the delta here, which are the three that we kind of pointed out in the data plots, and you see a whole bunch of other ones. So kind of our goal here in understanding the Qcd spectrum is to use scattering theory and phenomenology to connect experiment to scattering amplitudes. Once we have those, we can compute spectral properties from these amplitudes. We can then classify these hadrons and learn patterns of QCD. And then ultimately, we then want to connect these patterns to QCD directly. And then that's the job of lattice QCD, which again, you got a brief intro to, and I won't talk much about, but this is kind of an active area of research that many of us are interested in and working towards. All right, so as an example of applying these general ideas, and we'll go through and kind of introduce these ideas more in detail, let's consider, we want to understand the deuteron, which is the simplest nucleus. It's a bound state of a proton and a neutron. And it's generally called the hydrogen atom of nuclear physics. Now, why is that? It's because it's the simplest nucleus you can make. You can study the general nature of two-body nuclear forces. This is where we learned a lot about Yukawa theory and kind of these exchanges that happen between the proton and neutron that form these strong interactions. And from here, we got a great deal of information about low energy nuclear physics. Here, we're going to turn the table. So instead of saying, okay, we know properties about the deuteron from, say, chemistry or some other type of experiments, let's just assume we have proton-neutron information and we want to look at its spectral content. And this is the approach we'll be taking here. And what can we gain from looking at scattering data of protons and neutrons in terms of the bound state it makes up, which is the deuteron. So we have kind of a spectral property checklist that we can think about. So its mass, its lifetime, what its spin is, so its total angular momentum, what its parity is. Perhaps we can get some information about the radius of this object, what's its electric charge, and maybe some other properties we're not even thinking of. So these are, we want to check off as many of these things as we can by looking at experimental data and imposing our knowledge of scattering theory. Here's a little pop quiz. One of these items you can determine right now, just based on the fact that the deuteron is a bound state of a proton and a neutron. Does anyone want to take a guess at which one of these you can tell immediately without having to know any numbers or anything? Let's see. Yep, so Amar says charge with a question mark. You should have said charge emphatically with an exclamation point because you are exactly correct. What is what is the charge of the deuteron? And we want to say either voice or in chat. It's not a trick question. Is it positive, negative, 0, +2, -2?
+1.
+1. All right. Yes. Thank you very much. So yeah, so the neutron is electrically neutral. The proton is positively charged. So in terms of the electron charge, we just call it +1. And yeah, so the deuteron has a positive charge. It's got the same electric charge as the proton itself. So in terms of standard SI units, it's 1.6 times blah, 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 whatever the hell it is. I don't remember. Particle physicists, we just deal with plus or minus ones as much as we can. Yeah, so we already know one of these. That's great. But now we want to learn more. How do we learn more? Well, let's look at low energy neutron proton elastic scattering. So here is the cross section. So this measurement of the reactions in barn. So this fancy unit that Vincent showed. The cross section of neutron proton, where you have a proton at rest and a neutron hitting it with some kinetic energy, which I denote here with a T, and the energy unit here is in keV. So this is kilo-electron volts. The blue points are actual experimental data, and you will be given this experimental data when Andre gives his discussion on data fitting, and I need to give Andre some of this data set that he's missing still. So I need to do that after this talk. However, this data here, these blue points are actual experimental data, and we can point you to a resource where you can actually download it if you wish, but we'll give you all the material you need. And this reddish band here is a theory fit. So I'm not going to talk yet about where this red curve is, but here you would establish some generic properties of low energy scattering of neutron and proton using scattering theory. You then fit parameters to this data set, and then you can plot the result, and you see we get really, really good result compared to it. So we notice some general features about it. One is that at very, very low energy, the neutron proton cross section is pretty much constant. And then as the energy gets towards about 10 kilo-electron volts, it then rapidly, well, not rapidly, depends on your definition rapidly, but then it starts decreasing and tends toward a very, very low cross section at very high energies. And then at extremely high energies, usually the cross section is measured in terms of millibarns instead of barns itself. So the big question is, how do we convert this experimental data to properties of the deuteron? This seemingly at first glance seems like it's an impossible task. You have no idea how to read this. Even just looking at this myself the first time, it's like, well, there's stuff hiding in here, but we're going to do it. And that's going to be the task that we now follow. So I'm going to start moving on to describing some basics of what we do in scattering theory, but maybe before I move on, field any quick questions. At the end of this, we can have a more general discussion and questions, but is there any kind of quick questions on some of the general things I presented here? I'll give a moment. All right. Well, then let's continue then and start now describing nuclear reactions. So the first thing we're going to do is describe the kinematics of protons and neutrons. And I remind everyone that we're in these funky units where H bar and C are equal to 1. So everything is in these kind of what are called natural units. So we're going to make some assumptions here, and this follows along from what Vincent presented on the general topic of isospin. Oh, I see there is a question here. So we get a question, what is the relation between the cross-section and the scattering amplitude? So here, let me go backwards. So here, I'm just giving you an approximate relationship which is that the cross-section is proportional to the scattering amplitude modulus squared. So the scattering amplitude is in general a complex number. So you need to take the complex conjugate times itself, or the complex conjugate times the amplitude. And this is what the complex, or like this is what the modulus squared is of the scattering amplitude. And then there's some prefactors here, which we don't really care about right now. If you want to know the details and derive them yourself, you can do that. I can point you to references. But in general, the cross-section is proportional to the modulus of the scattering amplitude squared. And then we see there's a raised hand question. You want to speak or?
Yes, hello, Professor. So I wanted to ask, in the graph you showed earlier, there's this bound state of n star 1440 something.
Yeah.
Yeah. So what exactly does this graph tell us about, this bound state n star? Is it like likely more stable, or like what exactly does it tell?
So this is a good question, and this gets into if the people who know me well will hear me say often, just because you see a peak doesn't mean that's the only state that's there. So there's not a one-to-one correspondence to a peak in the cross-section and this pole behavior of the scattering amplitude. So here you do see that type of behavior. You see an enhancement near the mass of the delta. That means this denominator is getting very small, so you get the enhancement. This is an example where the cross-section, looking at just the cross-section, you can say, oh, here is where the amplitude has this type of behavior. This example here, and this gets into kind of a bigger discussion. The cross-section itself wouldn't really suggest that there's a state around here. Just based on all these other structures, you would say, well, there's probably nothing around here. But if this is a very complicated interaction, there's many things happening, and there's many other particles that are involved in the scattering process, in that you can have a pion and a proton interact, but you can create, say, two pions and a proton, or an eta meson and a proton. You can create a whole bunch of other stuff. All that stuff feeds into this cross-section here. So you get a bunch of interference from a whole bunch of other physics happening, which conspires such that even though you don't see anything in the cross-section here, when you do a detailed analysis, and I will not discuss that detailed analysis here because it's very long and arduous, and you can look at papers that do this professionally, and there's still some debates on many of these states. When you do the analysis and you separate out all the physics you can into its kind of fundamental base kind of objects, you'll find that the scattering amplitude for this object, even though the cross-section doesn't show this behavior, the scattering amplitude itself shows this behavior around this point. And this is where states like this can be identified. So, we see a whole bunch of states here. All of these states are encoded inside of here. But how many peaks do we see? 1, 2, 3, 4, 5, maybe 5 or 6 or so. So looking at the cross-section alone, looking for peaks, gives you a first kind of glance look at what interesting structures are here. But you really need to go through the scattering theory, which is all the stuff that I'll be talking about here. You need to go through all the detailed analysis to make the connection between experiment and this type of behavior, to where you can say, okay, let's now plot these masses with their various quantum numbers, and you get this plot out. Does that answer your question? I hope.
Yeah, thank you.
You're welcome. Okay, it's a very good question. And if you do work in spectroscopy, it's an important point that even though, there's a lot of good spectroscopists out there, but there's still some old ways, especially for people who don't necessarily work in spectroscopy directly. There's some old notions that a peak is a particle, and that is something that we want to do better than that. We want to quantify these things rigorously. Because we're physicists, we want to do, good physics. All right. So now let's get into describing these reactions. So the proton and neutron are nearly degenerate. Their masses are almost equal. So we generally call these things two different isospin projections of a bigger object called the nucleon. So the nucleon here is some object which has two components. The upper component is the proton and the lower component is the neutron. Sometimes I'll talk about the proton and neutron directly. Sometimes I'll talk about the nucleon. If I talk about the nucleon, really I mean either the proton or neutron. If I'm talking about the proton or neutron, I'm talking about them specifically. So let's make some first approximations, and you can always lift these approximations later in order to do better precision experiment. For the purposes we're doing though, we can go kind of very a bit more crude on some approximations, which do a really good job because we're not after precision physics here. So the proton and neutron mass are almost equal. So the first approximation is, let's assume the isospin limit, which the isospin limit is just a fancy word for saying that the proton and neutron have the same exact mass. So we'll call this mass, instead of distinguishing between P and N, we'll just call it M. And this in general is the nucleon mass. And roughly it's 940 MeV. For all the exercises I give and for all the analysis that I'll show here, I won't worry about a bunch of decimal places. We'll just need to get rough approximation where some things are. And then you yourself, either out of sheer curiosity or you work in this field, you want to do something better, you can add as many decimal places as you want. But always remember, this is an experimentally driven science. That's what physics is. So there's always some sort of uncertainty based on some measurement or something. So for here, let's just stick with 940 MeV for the proton and neutron mass. We're going to consider in general relativistic reactions. For very, very low energy of neutrons and protons, you can get away with non-relativistic reactions. However, in general, Qcd spectroscopy really is a relativistic field. So let's just build in the relativity effects from the start. There's not much that really needs to change, and it works for any kinematic regime. So the nucleon has a momentum P, which I'll use P for the momentum, and it has an energy, which I'm going to label here with omega. And you may say omega, that's a weird symbol for energy. However, if you've taken quantum mechanics, you may, and electromagnetism in, say, your undergrad degrees, for those of you who have, you know that frequency and energies have this intimate relationship. There's maybe H-bar factors that relate them. So I will use omega for the single nucleon energy, and later on we'll introduce a more conventional notation for the two particle energy. Anyway, in relativity, the nucleon energy is given by the square root of the sum of the squares of the mass and the momentum. So the momentum squared here is simply just the magnitude of the, since this is a vector, it's got x, y, and z components. You just take the magnitude squared and you add it to the mass squared, and this is the energy of the nucleon. If you were interested in very, very low energy physics, then you can look at the non-relativistic limit, which is when the momentum scales are much, much smaller than the mass. And you can expand this out to where the energy is given by the first term plus the first term, which is the particle mass, plus p squared over 2m plus some other correction terms. This second term may look familiar. This is simply the non-relativistic kinetic energy of a particle. And indeed, this helps motivate the definition of a particle's kinetic energy. The kinetic energy of a particle is given by omega, its energy, minus m. So the relativistic kinetic energy is all of these terms from this expansion here. We're simply taking this minus m. And then in the non-relativistic limit, this gives you back what you know as p squared over 2m, which you can show then is equal to, mv squared over 2, or whatever the in terms of velocity is. So your first exercise. Now, throughout this discussion here, I'm going to pepper with little exercises. Some will be very, very simple. Some will be maybe not so simple. They are not mandatory by any means, but I would encourage you to try out some of them. You don't need to do all. If you do all of them, great. Then you're, hopefully catching on and learning something. Or, you're someone like me who's done this all before and say are bored and want to do some easy exercises, but I don't want anyone to feel discouraged. I don't want anyone to feel like this is necessary. Pick some exercises that you find interesting and give them a try. If you do more, great. If you don't, it's whatever. This is not a strict, rigorous course. But the first exercise here I'm suggesting is to prove this non-relativistic expansion from here. So if you know Taylor series, this is exactly where this comes in from. So we discussed the kinematics of a single nucleon. It's got some momentum and got some energy. What if we put two nucleons together, so a proton and a neutron? Well, that's simple. The total momentum, which I'm going to denote here by capital P, is just the sum of the neutron momentum and the proton momentum. So here the neutron momentum I call P1, the proton momentum I call P2. And if, let's say, you know what the total momentum of the two particle system is, and you know the momentum of one of the particles, the momentum of the other particle is simply the total momentum minus the other particle's momentum. Simply, if you put this to the other side, the total momentum is the sum of both momenta. So that's the total momentum of the two nucleon system. And the total energy, which I'll use here as E, which you would think is a more suitable term or variable for energy, is simply the sum of the individual particle energies. So single particles have an energy and the momentum. If we consider two particles at the same time, I want to describe what we call the system of two nucleons, the system of two particles. We can simultaneously describe them by a total momentum, which is the total momentum of the two particle system combined, and a total energy, which is the sum of the two energies combined. Now, in general, these are the general frameworks. However, there's some very special reference frames that we can analyze the system in. If you remember from your early physics, whenever you start describing some physical process, you define some reference frames, some X, Y, and Z coordinates, say, to describe, to start attributing, different angles and different points in position with respect to an origin of these various kinematic quantities. There's a very special frame to work with two particle systems, and it's called the center of momentum frame. So what does this mean? Center of momentum frame is a frame in which the total momentum of the system is 0. So here, P is equal to 0. So the total momentum is equal to 0. We use a star to indicate that any kinematic quantity that has the star notation is evaluated in the frame of where the particles are going back to back. So sometimes this is called back-to-back frame. Sometimes this is called the two-particle rest frame. Sometimes you may call this the center of mass frame. However, in relativistic physics, center of mass is actually different than center of momentum, but that's a technical point. If you want to be loosey-goosey with language, it's you're meaning the same idea, where the center of momentum frame is the frame where the two particles are going back to back. So here, the neutron has a momentum P1, which we will call this momentum in this frame only a special symbol called Q. So I don't want to write ones and twos everywhere. Let's just use Q. And particle 2 will have a momentum minus Q. So when you add the two momenta up, you get 0. The total center of momentum frame energy, if you evaluate P1 and P2 in these star CM frames, is simply twice the square root of m squared plus q squared. From here, we now have a restriction that relates the momentum of the particles and the energy of the particles. So in the special frame where the total momentum is 0, let's say we want to describe everything in terms of the total center of momentum frame energy. Well, then we would have energy as our variable, and we can fix Q by the energy. And when you do that, you can solve this equation and show that Q star must be equal to 1/2 the square root of E star squared minus 4m squared. So in this way, you can either give me the momentum in the center of momentum frame of the particles, and I can give you what their total energy is, or You give me their total energy, and I'll tell you how much momentum they have. Excuse me. Another exercise. Show this relation is true from here. And this is where some simple programming skills come in the language of your choice: Python, C++, C, Fortran, Perl. I don't care. Plot this function as a function of the energy. I want you to take a look at what it looks like. All right, so this is the description of two particle systems. You have some total momentum and some total energy in the special frame of where the particles are going back to back. We are fixing the total momentum to 0, so that's nice. So that leaves out those degrees of freedom. And then the momenta of the individual particles, the magnitude of the momentum, which is this Q star here, is fixed by the total energy. So the degrees of freedom here are the energy or the momentum, either one, and then there's a remaining degrees of freedom, which is the orientation. I'm not going to talk about the orientation now, but essentially these two particles can be oriented however they want in space. Later on, we'll pick some definite directions to describe the reaction kinematics. So for two particle systems, they can't have any energy they want. And this restriction of, we have a question before I go on. So what if P and N are moving in the same direction? Do we still need the CM? So the center of momentum frame is defined as a frame where the proton and neutron are moving back to back, opposite directions with the same magnitude. If they're moving in the same direction, then you are not in the center of momentum frame. So you can think about so here in this frame here, so here I'm in a different reference frame where the particles are moving with some total momentum, capital P. And in this case, both particles are moving to the right. So, they're not moving exactly to the right. They have some, up and down direction, but they're both moving in the same general direction. So this is a valid reference frame to describe everything in, and you could do this. And there is another reference frame which we will use later called the fixed target or the lab frame that a lot of experiments use that uses an asymmetric definition. However, the asymmetric definition, this general moving frame, you need to specify what the total momentum is, and then the total energy is, and then how it distributes amongst the two particle system. So there's nothing wrong with that, completely valid. The center of momentum frame is a special reference frame. So now let's imagine you are moving at the same speed such that your total momentum matches with the two particle system. Well, then if you're doing, and this is the essence behind relativity, if you're moving at that same velocity, well, then the two particle system is not moving with respect to you. They are just moving apart from each other. So the center of momentum frame is just a special frame that makes it easy to analyze reactions. So you don't need to if you don't want to, but it makes it easy to analyze everything because you are restricting some of the degrees of freedom to a specific point, and then you can describe your system in a more simple way. There is a way to then relate these kinematic variables here, so E and Q with this P star equals 0, you can then relate these rest frame, excuse me, kinematics to a general moving frame. I won't talk about that here, but essentially it involves transformations which relate different kinematic lines together. But I won't talk about that here, but they do exist. So this is just a special frame to describe kinematics. So the two particle system can't have any configuration of energy and momentum at once. It needs to obey certain restrictions set forth by energy and momentum conservation. This restriction of kinematic configurations is called a kinematic phase space, which is all the available space of any kinematic configuration subject to energy and momentum conservation. I put a warning here because there's some very heavy mathematics I'm about to show, but we need one of these quantities to study the scattering amplitudes, and I don't just want to give it without some physical motivation for it. So if you're very keen on mathematics, you can go through and look up the stuff in detail and show all the proofs that I'm going to kind of just jump over. If you're not keen on it, I'm going to talk for 30 seconds to a minute or so about this, and then we'll give a formula for a specific thing that we need. But I don't like just giving a formula without some sort of justification behind it. So here we go. This is the phase space to describe relativistic two-particle systems for any kinematic configuration that you want. And there's some key terms in here. These last two terms are differentials, which describe all the distributions that each particle can have. So you have some small element in X, Y, and Z for particle 1, small element in X, Y, and Z for particle 2. And then because it's relativistic physics, and I won't go into details here, there's some energy factors in the denominator. There's a bunch of 2 pi factors floating around. That's just a convention that particle physicists like to use nowadays. There's 2 other terms which use a fancy mathematical object called the Dirac Delta function. The Dirac Delta function is such that if the condition inside of it is 0, so in this case here, when P is equal to P1 plus P2, then this delta function is non-zero. If this condition doesn't hold, then it is 0. So here you have 2 restrictions. You must have momentum conserved, and you must have energy conserved. So the total energy must be conserved and the total momentum must be conserved. If they're not conserved, then the argument inside here will not be 0, and then these delta functions are identically 0. So here you must conserve energy and momentum, and here you have the various distribution the particles can take. You can then do a bunch of mathematics, which I'm going to skip over, and you can rewrite this into a form given by here, where you can simplify this if you evaluate it in the center of momentum frame, where this whole big thing is going to be equal to twice rho, which is some kinematic factor I'll mention in a moment, times what's called the step function, which this says if the argument of this theta function here is greater than 0, then it's 1. If it's less than 0, then it's 0. So all this is saying here is that you must have the energy for the 2 particle systems greater than the rest energy of both particles. This rest energy is called the threshold energy, which is just if you have 2 particles sitting there, their total energy is just twice their mass, or it's the sum of their masses, which here is just twice their mass. So it's twice the proton nucleon mass. So you must have energy greater than the trivial system not moving. And we often give a special symbol, ETHR, for threshold energy is twice m. At this point, Q star is 0. So the momentum of the 2 particle system is 0 at this point. You can show that. So for the nucleon at 940 MeV, the threshold energy is roughly 1880 MeV. Then you have an orientation. So this is the other degrees of freedom that I didn't mention, where the 2 particle systems are back to back and they can have some energy and they can be oriented any way you want in the space. This thing is just some remaining degrees of freedom. The last quantity here is this rho factor here, which is simply the 2-body kinematic phase space factor. This is a factor that appears all the time in the scattering amplitude equations. So we need this factor here. But the motivation for this factor is this just tells you this is some prefactor that goes along with describing the distribution of 2 particle systems. All right. So we'll need that factor later. Here is the justification for it. Here's an exercise. Plot this function as a function of the center of momentum frame energy. A bonus exercise for those of you who are ambitious is to derive this factor from the starting point. Again, these are suggestions. If you've done it, if you've taken quantum field theory, you've most likely done this exercise. All right. So we have the kinematics of single particles and 2 particles. Let's go on to describe the kinematics of binary reactions. So now we have a 2-particle system with some initial energy and momentum. It evolves in time, something happens, and then the outgoing particles are a proton and neutron with some final total energy and momentum. So now we want to describe what this binary reaction is. And it's actually quite simple once you have established all these other previous quantities that we did. So total energy and momentum must be conserved. So this is a general property of all scattering reactions that must hold. Total energy and momentum is conserved. This means the total initial energy must be the total final energy, and we'll just call that E. The total initial momentum must be the total final momentum, which we'll just call P. Great. So we've reduced these 4 kinematic variables to just 2. Now we can analyze the whole system in the center of momentum frame. So now P star is equal to 0. Well, since P star is equal to 0, the initial and final states are both at rest, okay? And we're going to consider equal mass scattering. So this means the initial relative momentum is going to be equal to the final relative momentum, which I'll just call this Q. So here is kind of a cartoon of this kinematic configuration. You have some initial neutron coming in with some proton coming in the negative direction. A reaction happens, and then the neutron goes out and the proton goes out. Now the angle that the neutron scatters from its line, so here is, say, the z direction, and now this neutron is at some angle called theta. This theta angle here is the scattering angle. This is the remaining degrees of freedom to describe a reaction. You have some total energy of the system, and then you have some scattering angle. In the following, we're not going to worry about the scattering angle and just assume that the interaction between the proton and neutron at very, very low energies is independent of the angular distribution. You can show that it's true in general for very, very low energy physics. As you increase the energy, there is an angular dependence, but we're going to ignore that and not talk about that here. So this is our kinematics of the binary reaction. We now just need the total center of momentum frame energy, which fixes the relative momentum. And we need the center of momentum frame scattering angle, which in this lecture series, we're going to just ignore for now. But in general, it's there. And for high energy physics, you need to deal with it. So again, you can show that E star must be related to Q star via this way. And I'll just remind you of these exercises, just show this result. So this is the same way that was done a few slides ago. So there's another frame which we need in order to relate to experimental data. So I'll introduce it now, and then we'll use it next time. And this is the fixed target or the lab frame. So instead of having everything back to back, we're going to now choose to where the initial proton is at rest. And this is what's done in a lot of experiments. You have some proton, some hydrogen gas that's sitting in some container or some tube or something. You shoot some neutrons at it, and then a scattering reaction happens, and then the proton and neutron go flying off. So the proton and neutron go flying off at some angles. The initial proton momentum is 0, and the initial neutron momentum is just the lab momentum. So the total energy then is given by this relationship here, which is just the energy of the proton at rest plus the energy of the moving neutron. And you can show that the kinetic energy of the neutron is equal to m squared plus p lab squared minus m. So that's just the energy of the neutron minus m, as we previously defined. There's a relationship here between the lab frame kinetic energy and the center of momentum frame momentum, which is 1/2 m Tn. We will use this result later because we need to use it in order to compare our results to data. If you want, you can take this as an opportunity to use this exercise here. So this is the relationship between the lab frame kinematics and the center of momentum frame kinematics. E star squared is equal to E squared minus capital P squared. You can use this relationship here to find the relationship between Q star and T. So there's this question earlier about what if you don't work in the center of momentum frame. This is the relationship to transform your variables into other frames. Okay. So that's all I'll say about the fixed target frame. I just want you to be aware of it. We'll use it later on. Right now, we're pretty much be focused on the center of momentum frame variables. So that's all about kinematics. I've already went on for about an hour. I wanted to introduce some concepts about scattering amplitudes, but maybe let's take some, if there's questions first, and if there is light questions, maybe I can start introducing some concepts of the scattering amplitudes before we break for the day. So are there any questions about reaction kinematics? So again, we need to describe we'll describe our system by really just one variable here because we're going to ignore all the angular dependence in these exercises. So there's only one variable that controls the kinematics of the reaction, and that's either the total energy in the center of momentum frame or the total relative momentum. Either one you use, they're related by this simple relation. So I see there's a question. So a bit lost on Q, what did it represent? So let's go back to, boom, 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 boom. So here we had our general kinematics, P1 and P2 in some general moving frame, capital P. If we set capital P to 0, so we look in the total center of momentum frame, then Q is just a definition for P1 in the center of momentum frame. Minus Q is just the opposite direction of momentum. So instead of writing P1 and P2, I can just write just Q here. And if I know the momentum of one, I automatically know the momentum of the other one because it's just in the negative direction. The magnitude of this momentum Q is just this Q here. So this Q here is just a special momentum. It's the momentum of the particles in the center of momentum frame. That's all that means. So instead of writing P1 and P2 out separately in the center of momentum frame, I can just write Q, and that will mean the momentum of both particles, since here I'm just writing the magnitude. I hope that answered your question. Okay. All right. So yeah, our binary reaction, we can either use this momentum of either the particles to describe the system or the total energy. All right, let's start introducing scattering amplitudes, and then we'll break. So scattering theory is now aimed to how do we constrain to understand the dynamics of this reaction. So we've already described it kinematically. How do we describe it dynamically? So subatomic particles require quantum mechanics in order to describe physics properly. Quantum mechanics relies on using probabilities. So the best you can do is just describe the probability for some event to occur. So in quantum mechanics, we deal with probability amplitudes. So here's an example here. Psi is some probability amplitude. It's some wave that is, it has some associated energy moving in time and some momentum in the spatial part. It's a complex number in general. You see here I, this complex number I, and it's got some magnitude here. This psi here, this quantum mechanical probability amplitude, which I'm just using some generic notion here, which you may have seen if you looked at the double slit experiment in quantum mechanics. In quantum mechanics, you generally call this as the wave function, which is the thing that encodes kind of how the system evolves. From the probability amplitude, you can get out the probability just by taking the modulus squared of the probability amplitude and then integrating over all the degrees of freedom that you're not looking at the probability distribution in. So it's important here that we are looking at a function which is complex in nature. And we will ultimately describe our scattering process by scattering amplitudes, which are a specific type of probability amplitude. So let's look at a mathematical intermezzo, and this is what I wanted to get through today. And that's complex numbers. So complex numbers are necessary in quantum mechanics in order to describe how quantum mechanical systems work. I'm going to kind of, if you've seen complex numbers before, this is just a very quick basics property intro. If you haven't seen quantum mechanics before, if you haven't seen complex numbers before, these next couple slides just serve as some useful relations to be aware of as we build upon our scattering theory. It's pretty much impossible to go through scattering theory and spectroscopy without knowing something about complex numbers. And that's pretty much true of most fields in physics nowadays. So a complex number Z, which we write Z as in the complex field here, you can write in its Cartesian representation as some real part X plus I times Y, which is the imaginary part. So X and Y are real numbers, and I here is the square root of -1. So this is the imaginary unit. There's some various properties to note of complex conjugation. So complex conjugation is if you have a complex number and you act this star operator on it. This is a different star than the kinematic star that we were talking about before. But the complex conjugation is such that you just flip the sign of the imaginary unit. So Z star is X minus IY, and it's got a property that if you take the complex conjugation of a complex conjugate, you get back Z. From the complex number and its conjugate, you can describe the real and imaginary parts, X and Y, in terms of a sum and difference of the complex conjugate and the complex number. So exercise, show these from these definitions here, show that the real part of Z star is equal to the real part of Z, and that the imaginary part of Z star, and that's that Z complex conjugate, is equal to minus the imaginary part of Z. Here are some algebraic properties, which I'll kind of just flash through, and the slides will be available for you to examine. It has some simple algebraic properties where you sum or take the difference and you just group them together by real and imaginary parts. The product is the same idea, except you use the fact that I times I is -1. So you get sign differences coming up and you can distribute it accordingly. And then divisions work by rationalizing the denominator by using complex conjugation. So again, just some properties to be aware of. There's also the polar representation where instead of writing as X plus IY, Z is some radial component times the exponential of some phase. So here we have the imaginary and real Z axes, complex number Z, so it's X plus IY. Its components in terms of the angle theta, the angle phi, which is measured from the positive real Z axis, and the radial component, which is from the origin to the point here, is the radius here. The X and Y components in terms of these two are just given by R cosine theta and R sine theta. I keep saying theta, phi, and this is just using standard trigonometric identities. And I bring us up here, you may know of the Euler identity, which is a very cute relationship between the exponential I phi and cosine phi and sine phi, and this links together exponentials and the trigonometric functions. This is often used quite a lot, and we'll use it later on. So if you're not aware of this identity, you may just want to brush up by looking at it. So we can write X and Y in terms of R and phi. You can also write the magnitude R as the modulus of Z, which is equal to Z times Z star, which is the square root of the sum of the squares, and the phase here, which the phase is sometimes called the argument. And there's a bunch of conditions on if X is greater than 0, less than 0, and if Y is 0 or not. And it's just given by this arctangent formula here. I won't go into too much detail. We won't use it too much. But if you want, here's an exercise from all these things here. Look at this complex number here, and then identify its real and imaginary parts, the magnitude, its phase using this horrible identity, and then verify all of these simple procedures numerically. All right. So that's the review of complex numbers, and I think I'll end it here now. So the next thing we're going to is like, okay, we have talked about the kinematics of these reactions to happen. We have introduced ideas of complex numbers, since everything here is quantum mechanical and quantum mechanics relies on complex arithmetic. So in quantum mechanics, the reaction dynamics are encoded in a specific probability amplitude called the scattering probability amplitude, which here I generically denote as S. So you have some initial state, which is some initial particle configuration. It evolves in time to some final configuration, and the evolution is given by this S probability amplitude here. For reactions, it depends on the energy, and in general depends on the angle, but we're going to assume low energy physics here. And the probability to go from this initial and final state is simply the modulus of the probability amplitude squared. So this is where I'll leave off. Next time, we will start introducing then how to relate this, how to find constraints on this object here in order to get some physics out from it. So I'll stop here and take any further questions. I know it's a lot, and it's a lot to try to cram in 2 lectures, but I'm really hoping this gives you kind of just a survey of what we do in spectroscopy, linking scattering to physics. Yeah, so Amar's asking the big picture. So the big picture, you're exactly right. Let me go back to this example here. So the big picture is you have some scattering data, so you measure some cross-section. You want to understand its spectral content, which ultimately understanding the spectral content is understanding where these pole singularities lie in M. So we need to know M. So we're going to use general properties of M in order to fit the cross sections to and get out these mass and width parameters. Now, how do we constrain M? Well, we need to be able to describe M, the scattering amplitude, and it's got two components. One, it's got the kinematics of the reaction, so it depends on the energy, and then it also has the dynamics, which we don't know the dynamics. Ideally, we like to calculate it from QCD. Here, we're going to infer the dynamics from looking at experimental data. And then ultimately, we're going to be able to connect this to the deuteron, since the deuteron, in the case of proton-neutron scattering, is hiding inside this data. And it's hiding in a weird way. But that's the overall goal. We're connecting scattering data that you get experimentally to some known properties of particles using a theoretical structure called scattering theory. I clicked the wrong thing. Whoops. Am I still here? Yeah, I'm still here. Sorry. All right, I stopped sharing. I didn't mean to, but I can share again. All right. So, are there any other questions or concerns, or just some general things you want to discuss?
Maybe while people come up with questions, just a reminder that for those of you that are enrolled in the mentoring program, we are going to have a meeting with the mentees in an hour, right? Was that 1 p.m. or 2 p.m.?
I thought it was 2 p.m.
I'm going to double check. You're probably right. Yep, 2 p.m. So in an hour and 40 minutes.
Well, either I scared everyone off, I was exceptionally clear, which I doubt, or this was boring, which is most likely true.
No, I think you were really clear. It would be a blasphemy for anybody to think that this content is boring. So, no way.
So we have a good question here. With spectroscopy, is it possible to find glue balls? That is definitely the hope. So a lot of the techniques that we use are to identify exotic type hadrons. So they've been used to find tetraquarks, pentaquarks, all these real states, and glue balls is one of the candidates that we want to try to identify. Glue balls are tough though, because they share a lot of properties, not dynamic properties. They share a lot of spectroscopic properties with other states that could be more conventional, like say meson systems. So one of the goals is, so we could have already say identified possible glue balls. It's just hard to tell from strict scattering experiments. So people, and here Raul and myself are trying to concoct ways in order to probe these scattering processes with external probes, such as what if you hit it with a photon? Can you get any sort of interesting structure functions out that are able to discriminate between a conventional meson and a glue ball or some other more exotic state? So that is definitely one of the goals that we have under this umbrella, QCD spectroscopy. It's a tough problem, and we're actively working on it. There's a couple projects that we're involved with on trying to answer this problem. That it's gonna take considerable effort, but it's we wouldn't be doing this if we didn't think it could be done. So yeah, it's a great question, and that is it possible? Sure. It's going to require a lot of work, a lot of combined efforts theoretically, phenomenologically, and then experimentally to find it in nature.
And we're going to write a paper on something closely related. That should be coming out soon, right?
Yep.
So. I should have said we are writing a paper.
Yeah.
I mean, if there's no questions for Andrew, I mean, those of you that are in the Slack chat, you can just post them there. It's always better if you post them on the general chat window so other people can see it, right? Probably whatever questions you have, other people have, and even if they might not have it, they might, it might trigger a thought. Reading your questions, and the answers are generally useful for a lot of people. So I see somebody said that the chat is disabled. What do you mean? I was referring to the Slack chat. So there's a so what? It's Priyanka asking about the chat in Zoom or the Slack or the chat in Slack. Got it. Sounds good. Yeah. All right. But my comment was about asking if you have any follow-up questions that were not addressed here, or you're seeing this recording after the fact. You can always reach us, including Andrew, in the chat that is in Slack. All right. All right, maybe we should call it a day. Why don't we give Andrew a big virtual round of applause?
I can't really bow sitting down. So
You did a good job.
thanks.
Also. Yeah. So
yeah. So hopefully, so next time we'll get into some more details of scattering amplitudes, and then some looking at the deuteron specifically.
Awesome. Well, I'm excited about it. So, all right. Well, take care, everybody. Hope everybody's doing well. I'll see you in a little while, in an hour and 37 minutes. All right.